Okay, so besides doing electron configurations, you're also going to need to know how to draw orbital diagrams. And fortunately, I know it's like a lot at this point that we've done, but it's like not that much different doing the orbital diagrams. It's just a tiny bit more information. And I also like to do it though, because I think it's like, it's a good visual for where these electrons are, how they're organized. So as you can see, I've got that handy little weird chart on the right. You will need these to draw the orbital diagram, because again, it's basically the same information. So the first thing you need to do is determine the number of electrons. So it's the same process. So we're going to do this for silicon. So if we look it up on the periodic table, it's got 14 electrons. All right, now we need to determine the number of orbitals, which we draw as boxes for these orbital diagrams, are needed. So basically, more or less, we want the number of electrons divided by 2, right? Because each orbital can hold 2 electrons. So about 7 boxes. So right there, 1, 2, 3, 4, 5, 6. But that would be 7, but we don't want to like draw part of a subshell. So we're going to draw 3 boxes there, even though we won't necessarily need them all. We'll find out when we're done. But you want to count the number of boxes, and if you draw too many boxes, it's okay. There's nothing wrong with that. And you also, but the other thing is to know that you don't want to draw part of a subshell. You have to draw the whole subshell. All right. So now we're going to fill the subshells. And keep in mind there's 2 rules for filling. The Pauli exclusion principle, which states that each orbital may hold no more than 2 electrons. And the important part here that we don't show in the electron configuration is that they have opposing spin. So in other words, an up and down arrow. And it's always an up and down arrow, so if you can remember that, that's all you need to know about the Pauli exclusion principle, and that there's 2 electrons only. And the other rule we need to know is the Hund's rule, and that's that the p, d, and f orbitals fill with a single electron of the same spin in each subshell before paired electrons fill. Now, we don't have this rule for the s subshell because there's only 1 orbital in the s subshell, so it basically can't happen that you'd have single electrons in 2 shells. All right, so now let's take a look at what this looks like when we start filling the subshells. So again, we've got 14 electrons. So 1 and 2, 1s and 2s are going to be full. So, and notice I put the name underneath, and it doesn't have the superscript. You could write the superscript if you want to, but you don't have to. This is just telling you what is in the box above. So 1s has 2 electrons, that's shown by the arrows in the box. 2s has 2 electrons, so those are completely full. 2p is also completely full. So we've got electrons in each one of these boxes. And then we've got, in 3s, there's 2 electrons. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now I'm not quite done. I just filled up the ones that I know are full, and now we've got to figure out what to do with the 3p orbital. And I'll give you a second to think about how these are going to go. Are they going to be in the same, 2 in the same, or are they going to be in 2 separate orbitals, and are they going to be up and down, or both up? There's 2 electrons, so there's 2 choices there. Okay, so this is basically showing you there's the first one, and there's the second one. So again, this is Hund's rule. We have the 3p subshell, and it's got the 2 electrons are going to go into 2 different orbitals. They're not going to go into the same orbital because they want to be as far apart as possible. And both these orbitals have the same energy, so they are a little bit happier being like in 2 separate ones. But they have the same spin, just because that is the most energetically favorable way for them to be, and electrons always like to be in the most energetically favorable way they can be. All right, now these here when we have P, D, or F orbitals that are partly full, we have what's called unpaired electrons. And that's like one good reason for drawing the orbital diagram, because this is something you can't see in the electron configuration. And it turns out that this is an important consideration because unpaired electrons want to be paired, and they will often, these are the ones that often react to form compounds. All right, so now we're going to do some more practice drawing orbital diagrams. We'll draw a diagram for aluminum. All right, so aluminum has 13 electrons. And again, we start filling like the 1s, and see here I wrote the superscript. So again, you should write the, whether it's 1s or 2s, whether or not you put the superscript is up to you for the orbital diagrams. But it's 1s2, 2s2, 2p6. So again, that's all the same. Those fill first. So those are the core electrons. And then aluminum is in period 3, which means that shell 3 is filling. So now we're going to look at what happens here. So we got 3s2. And at that point, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. We need one more. So 3p1. There's just going to be one electron there. Okay, so now we'll do some more orbital diagram practice with the same elements that we drew electron configurations for just a couple slides ago. All right, so first of all, magnesium. And again, if you want, it might be a good idea to write the electron configuration first, and then you can just write it underneath. Again, the superscripts aren't necessary, but it does kind of help, I think, to show like how many electrons you need to put. So anyway, here's the diagram for magnesium. We've got 1s2, 2s2, 2p6, and then 3s2 for 12 electrons total. Now fluorine, again, has an atomic number of 9. And so when we put in these in the orbital diagram, we've got 1s2, 2s2, and then that's 4 electrons. We need 5 more. So we're basically completely filling like each in the p orbital. Like there's only one that doesn't have a doubled up electron. So again, that's an unpaired electron, and that's an electron that's really going to want to react. And fluorine is in fact a very reactive element. All right, now helium is just 1s2, just one box, so that's like obviously the easiest one to draw. And then here's argon. And this is about the biggest one that I would expect you to draw. Like I'm not going to expect you to draw orbital diagrams for period 4 below, so it luckily doesn't get any harder than this. So anyway, it's 1s2, 2s2, 2p6, 3s2, 3p6. So again, it's complete. Everything's completely full, and that's a very stable electron configuration, and argon is therefore very unreactive. Okay, now I'm going to show you how to do a electron arrangement of ions, and the reason we're going to do this is I'm going to show you why elements behave the way they do, because they tend to form ions so that they achieve a noble gas configuration. Let's start with sodium, which tends to form ions of +1, so it's Na+. If there's like a 1 there, you can either leave. Sometimes it's written and sometimes it's just assumed that it's 1 and not a different number. So it's Na+. So how many electrons does Na+ have? Now, this atomic number of sodium is 11. And if we have Na+, that loses 1 electron, so it's got 1 less, so it's got 10 electrons. So now that we have the 10 electrons, we're going to start filling subshells. And this is what we end up with. 1s2, 2s2, 2p6 is the electron configuration. Sodium that's not an ion also has a 1 valence electron in 3s1. Notice that one is missing. And now sodium has exactly the same electron configuration as neon, which, as we know, is a very stable configuration. So this is why sodium tends to form ions of +1. In fact, it's the only kind of ion that sodium forms, and it would much prefer to be that way than as an element with all of its electrons. Now let's look at fluorine, which likes to form ions with a charge of -1. Fluorine has an atomic number of 9. So F minus is going to have one more electron than 9, or 10. Now notice that's the same as Na plus. And we start filling subshells, and since we have exactly the same number of electrons, we end up with exactly the same electron arrangement, which is that of neon. So fluorine achieves a noble gas configuration by gaining an electron. All right, and now we'll just do one more example with silicon, which is a metalloid, which means that it can gain or lose electrons. So first of all, let's take a look at the atomic number of silicon is 14, and it can gain or lose 4 electrons. So if it loses 4 electrons, it's going to have 10 electrons total. And again, that's the electron configuration for neon. Silicon can also gain 4 electrons, and these are both types of ions that silicon tends to form. And when it does that, it has 18 electrons, which is the same as the noble gas configuration for argon, the next larger noble gas. So either way, it achieves a noble gas configuration, and either it can react either way. All right, we're pretty much done with electron arrangement. The one thing that I do want to mention is that everything I've shown you is for electrons in ground state. Now, if you remember from the previous lecture, if light strikes an electron, it can cause it to bump up to a higher energy level. And it can basically bump up to any energy level. So there's really no way to predict what that will be, at least not anything that you would learn in Chem 101. So you would not need to know this. The only thing you do need to know is that when it's excited, it's not in the same nice, neat configuration. The electrons can be anywhere. But since this is unstable, it will fall back to ground state. When we do have an excited electron, and this isn't something you would need to know how to do, but there's usually an asterisk there, as shown on the bottom here, and it's showing that there's an excited electron in 3p1 in this case, and then the electron got bumped out of 2s1. So again, this would be unstable, and this would quickly fall back to magnesium with electrons in the ground state. All right, so that's about it. I'll just summarize what I've said in this lecture. 1, electron's location can be identified by 3 different pieces of information. The principal quantum number, the subshell, which is S, P, D, or F, and the orbital, which is in the subshell. So the orbital is kind of like the house number. The subshell is kind of like a street, and the principal quantum number is kind of like the city. And all of these pieces of information tell you where the electron is. Orbitals flow from the lowest energy to the highest, and each orbital can accommodate 2 electrons of opposing spin. That's the Pauli exclusion principle. S, P, D, and F subshells have 1, 3, 5, and 7 orbitals each. And then we also have Hund's rule. The orbitals fill singly first with electrons of the same spin before filling with a second electron. And then finally, an element's position on the periodic table indicates its electron arrangement. That's all.